In today's tutorial, you are going to learn how to code a dueling Deep Q network in the Keras framework. We're going to use it to land a lunar module on the surface of the moon using the lunar lander environment from the OpenAI Gym. You don't need any prior experience with reinforcement learning, you just have to follow along. Let's get started. Before we begin, a couple of housekeeping items. First of all, if you're new here or if you've watched a few of my videos, please hit the subscribe button with the notification bell. That would help me out greatly and I would really appreciate it. Second of all, if you want to learn how to read deep reinforcement learning papers and turn them into functional PyTorch code, then I have just a sale for you. My course DBQ Learning from Paper to Code is on sale right now through Udemy for $10.99 for the next several days. My apologies, they have kind of done away with a $9.99 sale option. I'm not trying to squeeze an extra dollar out of you guys. It's just the downside of using a platform like Udemy is I give up some control over pricing. But hey, it comes with a 30-day money back guarantee. So if you don't like it, you can get your money back, no questions asked. All that said, let's go ahead and get started. So we'll begin with our imports. We will need TensorFlow. And, you know, I said Keras, we're going to be using the Keras interface. I guess technically it's really TensorFlow 2.1 more precisely, but they're kind of the same thing now. So it's, you know, using the TensorFlow backend. We need TensorFlow as Keras. That'll handle our layers. We'll need our Atom optimizer. The original paper used, what was it? They used RMS prop, which you can use as well, but I tend to gravitate toward Atom for most purposes. And we'll need NumPy to handle NumPy type operations. So I'm going to split this into a few different classes for the purposes of modularity and for keeping in accordance with the principles of object-oriented programming. So we have our Dueling Deep Q Network that handles the estimation of the action value function, as well as the replay buffer that keeps track of the state, action, reward, new state, and terminal flag transitions. That facilitates the training for our neural network. And then we have the agent class. The reason I split it up this way is because an agent is not a Deep Q network. An agent is not a memory, but an agent has a Deep Q network and it has a replay memory. And it uses those things to do things like choose actions and to learn from its experiences. So we'll start with the Dueling Deep Q Network. And Keras has started doing this thing where, or maybe they've done it all along and I just didn't know. I've never been a huge fan of Keras, but we are driving from keras.module and with our own class where we define our own feedforward function. One of the cool things about Keras, one thing I do like, is that I don't have to pass it the input dims because it infers that based on the shape of the input. That's pretty cool. So all I have to pass in are the number of actions and the number of dimensions for my first and second fully connected layers. Now I need to call my Dueling Deep Q Network superconstructor. And then I can go ahead and define my layers. And so that is keras.layers.dense, and that is FC1 dims. Now, whatever the FC1 dims are the output dims for the layer, and it'll just infer input dims. And we need a ReLU activation. We'll have a second dense layer as well. With a ReLU activation. Now, what makes Dueling Deep Q networks different from regular Deep Q networks is that in a regular Deep Q network, you would have something like self.q, and that's your output layer, and that would have a number n actions for the outputs, and that would be the end of the story. But for Dueling Deep Q networks, we split up the output into value and advantage stream layers. So we have self.v, that's the value. That is a Keras layers dense. And that just is a single output. The reason is that it is the value of the state or set of states. You can think of it this way, where the value of the state in which you're about to win the game is worth much more than the value of the state in which you're about to lose the game. So the deep neural network can learn that over time by sampling rewards from the environment, and that is encapsulated in the output of this layer V. And there is no activation for that. Activation equals none because we want the raw value. If it's negative, we want it to be negative. If it's positive, we want it to be positive as well. And we also have an advantage layer. Now, the advantage layer kind of tells you what it is. So it's the advantage of each action given you're in some state or set of states. So it says, you know, for one action, I think I'll get this feature reward, and for another action, I think I'll get that feature reward. So it encapsulates the idea that for a given state, different actions have different values. And that needs n actions output and no activation, because we want the raw values. So we have a couple other functions, and this is one opportunity for you to clean up my solution. So I'm going to overload the call function for this. It's kind of like the feed forward from PyTorch, but I'm also going to have a separate function for just getting the advantage layer out. And the reason is that when you do training in Keras, it expects the inputs, the X, as well as the labels, in this case the Y or the target values, and it will pass those states through the deep neural network, compute the output, compare it to the Y's, and then do whatever loss function you tell it. So the consequence of this is that the feed forward function has to perform a transformation on V and A, because we are interested in Q, which is a combination of the value and advantage stream. It's not just the addition. You'll see it in a second. We have to perform the non-trivial transformation from V and A to Q, because we're going to be passing in something with similar dimensionality for our targets. So, but then conversely, when we do the action selection, in the paper at least, they just use the advantage stream. The way I think about it, I could probably get away with using Q, because it's just going to be kind of proportional to the sum and then some other constant values. And so it's probably okay to use the Q, but I'm going to be consistent with the paper just to be on the safe side. So our call function is basically the feed forward from PyTorch. And we're going to pass in the state of the environment and pass it through the first dense layer, pass the output of that through the second dense layer, and then get the V and A. And notice X gets activated here, and I'm passing that into both V and A. So V and A share the common input layers, and they are two separate outputs to our deep neural network. And then we have the non-trivial combination of the two. So if you read the paper, there's a few different ways of doing it, and they have to do it for mathematical reasons, where just adding together V and A isn't identifiable, because you could add any constant to it, and so it would give you the same relative results. So we have to do something a little bit different and say Q equals V plus the quantity A minus tf.math.reduce mean. The reduce mean is why we needed the to import TF. We want to take the mean of A along the first axis, keep dims equals true, and then return Q. So what we're doing is taking a linear combination of V and A in a non-trivial way. In particular, we're subtracting off the average value of A, so the average advantage. But I don't just want that. I also want a function to just get the advantage out, and so we'll say X self.dense1 on state X A equals self.a X return A. So we'll use that for choosing actions. So I'll say may be unnecessary, please experiment with call. Okay, so I'll leave a little note there for your exercise as the reader or viewer. But that is it for our Dueling Deep Q Network class. So as I said, we have another class, and that is the replay buffer. Now, the purpose of the replay buffer is to store the state, action, reward, new state, and terminal flag transitions in the agent's memory, because temporal difference learning with a single step is incredibly unstable due to the fact that the Q function has a very complex dependence on the input parameters, so you end up wandering around parameter space in areas you haven't been to before, and you get lost, is essentially what it boils down to. So we need our replay buffer, and the replay buffer fixes that by having the agent sample a bunch of non-correlated memories so it can get broad sampling of the parameter space. So we need a max size. This memory doesn't grow unbounded. It has a max size. And this does require an input shape. Now, there are a number of ways of doing this. A lot of people will use something called a DQ or a DEC. I don't quite know how it's pronounced. It's a built-in Python data structure. It's basically a linked list. And has a property that when you append stuff, it goes onto one end. And then when it runs out of max memory, it starts popping stuff off the front. So it's kind of a first in, first out data structure, almost like a queue, but it's a linked list. I don't want to use that because then when you dereference it, when you try to get the state, action, reward, new state, and terminal flags back out of it, you have to remember what order you stored them in, and it just makes for messy code. So I like to do it this way where I say I have some max size, I have a variable for keeping track of my first available position of memory, and then I have a bunch of NumPy arrays. And for the state memories, we're going to have float 32 because these are floating point numbers. And we also need to keep track of the new states that result from the agent's actions. Reason being that this is all manner of DBQ learning is a model-free learning method, and so the agent doesn't know anything about how acting on the environment will affect the environment, and you learn it based on observing these state transitions. It's a model-free method. We also need an action memory, and that's int 32. We need a reward memory. And that's float 32 because those are floating point numbers. And a terminal memory. And we're going to leave that as NumPy bool. And the reason is we get Boolean flags from the environment, so we may as well leave them that way in the memory. We need a function to handle storing new transitions into the memory. Reward, new state, and done. Now the first thing we have to know is what is the position of the first unoccupied memory so that we can store the memories there. And that's given by memCounter modulus memSize. And then once we know where, we just go ahead and save it. It would be helpful if I ever learned how to type. Equals done. And very important, we want to make sure we increment our memory counter. Otherwise, we're just rewriting the same memory over and over. We're almost done. We need a sample buffer function. And that'll take a batch size as input. So what we want to know is, since we're initializing our memory with a bunch of zeros, it really wouldn't make sense to learn from an array of zeros, would it? What are you going to learn from that? Nothing. What you want to do is you want to learn from the set of already saved memories. And so you want to know whether or not you have filled up all the way to the end of the memories, in which case you're free to sample anything in that range, or you have sampled some subset of that, or filled up some subset of that. But you don't just want to use memCounter because memCounter can be greater than max memSize, and then you'll get, in C you would get a buffer overflow error. But here you don't. You just get a range out of index out of range error or something like that. So we need to do the minimum of the memCounter or the memSize, and then we have the batch random choice. So what this will do is it will sample batch size number of integers in the range 0 to max mem with replace equals false. That means that if you sample a memory, you can't sample it again. Very important. Then you want to say self.state memory sub batch Good grief. And then you just want to return them. I call it new states here, new states and dones. Okay. So that is it for our two kind of helper classes. Now we can turn to the harder problem of coding up our agent. So recall an agent is going to have a number of properties, including the memory as well as the DBQ network. So yeah, the first thing we want to do is define our constructor. And that will take a learning rate gamma. If you're not familiar with gamma or reinforcement learning in general, agents have the problem that they don't know how certain feature rewards are. So if I tell the agent, hey, the reward for the next state in that transition is, whatever, the agent doesn't really know if it's ever going to make it to that state because, life is uncertain for us as well as, reinforcement learning agents. And so they will discount that reward by some amount. $1,000 today is worth more than $1,000 in the future, even totally discounting inflation, right? Because 1,000 today is certain and 1,000 in the future is not. You might get hit by a bus tomorrow, who knows? Although probably not if you're self-isolating right now, which you should be. But gamma is a hyperparameter that determines to what extent they discount future rewards, and it's usually between 0 and 1, something like 0.99 down to 0.95. We also have the number of actions, epsilon. So epsilon is another hyperparameter for our agent. The agent has the dilemma. So it can do what it thinks is the best action for the given set of states or state it's in, but how does it really know that that is the best action? It has to spend some amount of time exploring the environment, testing out its assumption about what is the best action so that it can actually learn what the best actions are. It's called the explore-exploit dilemma. There are many solutions to it. Q-learning uses epsilon greedy. It means that we pick a random number, some fraction of the time where it's less than epsilon, we take a random action. If the random number is greater than epsilon, we take a greedy action. There is also input dims. We'll need that for our memory interface. An epsilon decrement. Now, epsilon does not stay large for very long. It starts out as 1 and decays over time to some minimum value. You can use any functional dependence you want. I'm going to do it linearly, and it's going to decay by 0.001 each step. And where it ends is this parameter, 0.01. You want to leave it finite because you never know that you do have an accurate estimate of the Q function. You always have to be testing to some extent or another. A max memory size for our memory. A file for storing our model. Of course, some default values for our deep neural network, and this other parameter called replace. Now, this is getting into the details of DBQ learning. Of course, in my course, I go through the papers and explain all of the reasoning for this stuff. But this parameter here, replace, is another hyperparameter of our agent, and it comes into play when we're talking about the online evaluation network and the target network. So in DBQ learning, we are using one policy, the epsilon greedy policy, to generate sample data for updating our model of the world. But our model of the world is updated based on the estimate for the purely greedy value, the maximal action for a given state or set of states. And so it's a temporal difference learning method, meaning it learns at every step. So if you're using a target value over here to update something generated with this over here, you're effectively chasing a moving target, and it results in model instability. And so the solution to that is to have two separate deep neural networks, one that you use to select actions, and the other one that you use to estimate the value of the states for updating your deep neural network. And you perform backpropagation on the one that you use to select states, the online evaluation network, and you periodically copy the weights from that network over to the target network. So that way, the target network changes much more slowly than the online network, and you basically slow down the speed of your moving target. It helps with model convergence. And that is encapsulated in this parameter replace. So it's saying that every 100 moves, we're going to replace the weights of our target network with the weights from our online evaluation network. So we need an action space. Now, the reason for that is, as I said, it spends some amount of time doing random exploratory actions, and this list helps facilitate that, making it much, much easier. Of course, we want to save a bunch of our parameters. .fname equals fname. Now we'll have a couple other parameters. We'll need the learn step counter. That's just how many times we've called the learn function. That relates to the replace function. And we'll need a memory. That'll take mem size and input dims as input. Yeah, I do have input dims there. And we need the, what else? We need a Q eval, Dueling Deep Q Network. That takes n actions, SC1 dims, C2 dims. Let me double check and make sure I didn't swap those. I did. FC1, FC2, and n actions. Let's do this. Yeah, put n actions first. Sorry, I occasionally do silly things. There we go. And this is our next network. And that, again, is the target network that we use to generate our targets for the cost function. So now we have to compile our models, self.q eval.compile, and optimizer equals atom, LR loss equals mean squared error. And we also have to compile our QNext, but this is just a formality. Formality won't optimize network. Self.QNext. There should be, yeah, sorry, I made a mistake. There, like that. That's a separate function. That would certainly trip an error. Yeah, okay. So that's it for our constructor. Now let's define a simple interface function between the agent and its memory. And then it's pretty silly, memory store transition. You know, I'm missing a something somewhere. Let's see. Store transition. Oh, that's why. Def store transition. There we go. So this is kind of one of the funny things about object-oriented programming, is that you end up with these interface functions that are just one line. You know, if you really wanted to put the replay buffer as a member of the agent class, I wouldn't argue with you too much. You would forego this type of stuff, but whatever. You know, I just try to be as pedantic as possible. Next, we need a function to choose an action based on the observation of the current state of the environment. As I said, we want to use epsilon greedy, so we calculate a random number, and if it's less than self.epsilon, we have a random action. By doing a random choice from the action space. Otherwise, if the random number is greater than or equal to epsilon, we want to take a greedy action. Now, we have to enclose the observation in brackets because it expects an extra dimension. We could also use np.newAxis. That would be acceptable as well. Self.q eval.advantage state, and then we want action equal tf.math.argmax actions axis equals 1 dot numpy sub 0. It's because it returns a tuple, or rather an array of arrays, or rather, sorry, it returns an array. You want the integer from the array. You don't want the array itself because the OpenAI Gym does not take arrays as input, it just takes integers. But regardless of how you select the action, you have to return it. Okay, so that is the kind of trivial functionality of our agent. Next thing we want to do is implement the hard stuff, so the learning function. And right away we were faced with a dilemma. So we filled up our memory with a bunch of zeros. And as I said, it doesn't make sense to learn from a bunch of zeros. You have a couple of ways of dealing with that. You can have the agent do a bunch of random actions and fill up its whole memory or some subset of its memory with random actions, and then after that perform learning. Or you can just say, if we haven't filled up batch size of memory, then just return, which is what we're going to do. That's the easiest way. Just return. And then this also is kind of wonky from an object-oriented perspective. The agent shouldn't have insight into the memory counter of its memory, but whatever. Next question is, have we executed the replace number of learning steps? And if we have, let's replace our target network. All right, now we have to handle the feed forward. So Q predicted the values of our current states. But of course, first, getting ahead of myself, we have to sample those. New states and dones equals self.memory.sample buffer. Self.batch size. Hang on, I will fix the formatting there. Something like that. Now we handle the Q predicted. Q next equals tf.math.reduce max self.q next states 1 true dot numpy. So what we're doing here may seem mysterious. We are passing in the next states, states underscore, into the target network, Q next, and calculating the maximal action. The value of the maximal action, not the index, the value, I believe. Is that true? Reduce max. Yeah, it's not an argmax, it's a reduce max. We're getting the value of the maximal action. And we're going to use that momentarily. But first, we have to copy our predicted network. And this is because of the way that Keras handles the calculation of the loss. And this is a space where you can improve on my solution. And it's because I'm not too familiar with the way Keras handles array indexing. It doesn't seem to follow NumPy's conventions where PyTorch does. So I have this kind of janky solution. It's clear it works, but it's not elegant. So we'll say for IDX terminal in enumerate dones, if terminal Q next sub IDX 0.0. So what I'm doing here is for each state in our batch, we're taking a look at the done flag and saying if the state is done, then set the value of that next state. If the next state is done, then set its value to 0. And the reason is, if you're not familiar with reinforcement learning, the reason is that the value of terminal states is identically 0 because the value function tells you the expected future value, the expected value of future rewards. And if you're in the terminal state, there are no future rewards, right? You're done playing the game, so there are no future rewards. Hence, the value of the terminal state is 0. Then you reset the game and you start over, but then you're in the start state, not the terminal state. And so I'm iterating over the list of the array of terminal flags and saying, okay, if the next state is terminal, set the value for that next state to 0. Then what we want to say is Q target sub IDX sub actions sub IDX. So equals rewards IDX plus gamma times Q next IDX. All right, so let's explain this. So what we're doing here is we are saying that the target value for each state in our batch for the action we actually took is equal to the reward for that time step plus gamma multiplied by the value of the next step. Now, why do I call it target? It's a target because we're doing an update to the estimate of the action value function, and the target is the direction that we're going to be moving that estimate towards. It's a target value that we're chasing after in terms of our estimates. And you want to bias that in the direction of the maximal actions for the next state because those are the most valuable. And that's what all this means. Then we go back to insert mode, of course, self.qeval.train on batch. And we have to pass in the states and that target value. And that is almost it. Self.epsilon. That handles all of the training. So epsilon equals self.epsilon minus self.epsilon decrement if self.epsilon is greater than self.eps min, else self.eps min. So what this does is at every time step it decays epsilon by a factor of epsilon decrement, and if it's going to go less than epsilon min, it just sets it equal to epsilon min. Somebody's trying to get a hold of me apparently. He can wait. The next thing we have to handle is learn step counter. So learn step counter, as I said earlier, is the number of times we have executed the learning step, and that tells us it's time to update the parameters for our target network. So now we just have two bookkeeping functions: save model, and we'll say qeval.saves model file def load model. And you know what? That tells me I probably need an import up here. Let's see. I forgot an import. Man. This is probably going to break something. From TensorFlow, Keras.models import load model. I think it's that. I guess we'll find out when I go to do my imports if it breaks. Okay. So this is it for the Dueling Deep Q Network. You know what? Actually, I'm leaving this as an exercise to you, the reader. I'm going to leave that in, and I'm going to get rid of this. If you want to, then you're on your own. Go ahead and figure out where that lives. Okay, so that is that. So now we want to go vim main Keras Dueling DQN lunar lander, and we want to go ahead and edit our main file to write our main loop. And so the first thing we want to do is enter insert mode from Dueling DQN Keras import agent. We're going to need NumPy. We're going to need Gym. And from utils import plot learning curve. And I don't think I need TensorFlow. We will start with our main loop. env equals gym.make lunar lander -v2. Endgames equals 300. You know, let it run 400 or so. There's a fair amount of variability between run to run, so letting it run a little bit longer may give more dramatic results. Agent equals agent, gamma 0.99, epsilon equals 1 to start, learning rate 1 by 10 to the -3. Input dims for our dimension is a list of 8 elements. 1e -3. I'm going to decrease epsilon by 1 by 10 to the -3 every step. Mem size equal 100,000. Batch size of 64. Epsilon n equals 0.01. Is that what I called it? I guess we'll find out in a minute. FC1 dims equals 128. Place 100. We need a couple of empty lists to keep track of the scores and the values of epsilon over time, so we can plot the scores versus number of games and also scores versus epsilon. So let's go ahead and play our games. I in range in games, reset our done flag. That equals false. Observation equals env.reset. And play the episode. Then take that action. Reward, done, info. That step. Increment our score. Store the transition in the memory. Underscore, done. Set the old state to the new state, very important, otherwise you won't be selecting an action based on the current state, but rather on the first state of the environment. And then call your learning function. At the end of all the games, or at the end of each game, sorry, append the epsilon history. Epsilon, and append the score. And to see if it's learning, take the average of the last 100 games and print some debug information. Score. Its average score. And the epsilon. At the end of all the games, make a file name, lunar lander, PNG. We need the x-axis for our plot. And plot learning curve, x scores, eps history. This plot learning curve lives on my GitHub. You can just do a git clone. It's not really worth going into the function. It's just a simple plotting function. So that is it for our main loop. Now it is time to test it. So we'll say Python main. See how many typos I made. Cannot import plot learning curve. You know why? That is because I have changed the name many times. So let's go into utils. And here I call it plot learning. Yeah. Okay. So let's go back here and just change the name here. And of course here. Let's try it again. Init missing one positional requirements, or one required positional argument and actions. That is in my agent. So that means here I didn't put an actions. Okay. And of course for the lunar lander environment there are 4. int32, that's because it's np int32. So vim dueling DQN Keras, that's on line 42. NP, yep. Okay. Try again. Agent object has no attribute batch size. That's because I forgot to save it. Name SLF is not defined. That's in line 111. Insert self. A lot of typos today. Agent abs no attribute epsilon min. I must have called it epsilon min. I called it eps end. Call it epsilon min here. There we go. All right, I'm going to go wander off, and we will see how it does. And we are back. That took a good 10-15 minutes or so, but it has finished running, and you can see it has effectively learned how to beat the environment. So if you take a look at the average scores, you can see that it does quite a bit of oscillating over time, but it does get up to the requisite limit of 200 points over the past 100 games to consider the environment beat. And if you take a look at the plot here, you can see that indeed the agent's average score over the previous 100 games has an overall upward trend with some oscillations. Oscillations are probably due to a couple of things. One, our learning rate may be a little bit too high. Maybe decreasing it by a factor of a half or so would help. And it could also be that the replace interval is too short, so we are still chasing a moving target that is going a little bit too quickly. So maybe 1,000 instead of 100 would do. But these are a couple hyperparameters for you to play around with. If you'd like to understand the how and the why behind everything I did, remember that my new course, Deep Q Learning from Paper to Code, is still on sale for $10.99 through Udemy. And I do read the entire paper for this. I show you step by step how to read the paper, how to understand it, how to implement it, and we go through it line by line together in PyTorch, not Keras, but PyTorch. I hope this was helpful. Make sure to subscribe and hit that bell notification icon, and I'll see you in the next video.